עדיין לא, כאילו, לא יודע, בעצם אולי אפשר גם את זה לכתוב, אז ליטית או משהו, אבל סתם כאילו סתם לא היינו בטוחים אם זה היה כאילו, אם היה חסר סוגריים או משהו טוב, זהו, אני אתייעץ עם נטע לחוות בעצם.
אבל לא מזיק לשלוח שאלה בפורום. אוקיי. Okay, so we reformulated the problem in several ways and we'll continue to do so. We now have this max-min problem. We added these additional parameters, alpha mu, p parameters, and we know that we can find a solution for the support vector machine criterion for the separating plane by minimizing with respect to W and maximizing with respect to alpha. Okay. Now, as you will see, this actually turns out to be useful, and you'll see why. So, in terms of the W's, we now don't have constraints. So in terms of the W's, the constraints involve only the alphas. So if we want to minimize with respect to the W's, we should just look for the derivative and ask that the derivative with respect to W is 0. This is really with respect to the elements of W. So we know that the dl to dwi must be 0. Okay, what is the derivative of L with respect to wi? So the first term, this is half sum of wi square, right? So what's the derivative with respect to wi? And here, what will we get with respect to wi? We will get minus sum over mu, alpha mu, y mu, x mu I. Right? So this should be 0. And this tells us that W is equal to the sum over mu, alpha mu, y mu, x mu. Okay, so we already found something useful, and this is that the optimal weights, I should call this W opt, maybe put it here too, that the optimal weights can be written as a combination, linear combination of the examples. Right? Moreover, it's not all the examples, as you'll see in a moment. So let's think about the fact that this should be a maximum with respect to alpha. So there are two possibilities. One is that we're really sitting on this constraint, that alpha is 0. But let's think about those alpha for which are not 0. If for some alpha for any alpha which is not 0, we're not sitting on a constraint, and then we need to be on the maximum of this function. The derivative with respect to alpha should be 0 in that case. If alpha mu is larger than 0, then dl to d alpha mu has to be 0. And that tells us that 1 minus y mu w transpose x mu is actually equal to 0, or in other words, y mu w transpose x mu is equal to 1. We already said this at the end of the last lesson that if, for those examples which are not at the minimal distance, those which are not where the distance is not, just the minimal one. Remember that this is the minimal because we renormalized the w. So those for which this is 1 are actually the examples that are closest to the plane. Those that are not closest to the plane, this thing is not equal to 1. It's negative. And for those examples, the alpha mu will end up being 0. Because if this is negative, if maximizing with respect to alpha will force this alpha to be 0. So the other side of the coin is that those alpha mu's for which are not 0 are those for which the example lies exactly on the. We say that this example lies on the margin. Yes.
For most of the time, could you just make it quick two-dimensional example?
Yeah.
To get the alpha and the.
Yeah. So I'm just saying, let's take an example like the one that I drew before. Maybe I will do this like this. Okay, so in that case, the separating plane is going to be something like this. Let's add a few more points. Okay. And these 2 points are at the same, okay, I didn't draw it very well. Do it like this. Okay, these 2 points are at the same distance from the plane, and these are the ones that will end up being in this solution, the ones for which y mu w transpose x mu is equal to 1 exactly. For the other ones, this will be larger than 1. And so these are the examples that we say are on the margin. And what we see from the math is that for those examples that lie at the minimal distance, remember that 1 is the minimal distance because we normalize, we used a normalization of w leading to this formulation such that 1 will be the minimal distance. So the points that lie at the minimal distance, for those points, alpha mu doesn't have to be 0. But for all the points that are outside, all these points, this for those, if alpha is positive, let's say if alpha is positive, we necessarily lie on the margin. We are on points that are at the minimal distance. Okay, if alpha is positive, and all the points that are not on the margin, alpha mu has to be 0. We see this from the maximization with respect to alpha. And therefore, the picture that we should have in mind is that at the solution, we will have a few points not on the margin, alpha mu for points mu not on the margin, alpha mu is equal to 0. And for points on the margin, typically alpha mu is larger than 0. What does this mean? It means that now when we go back to this conclusion, that W is a sum over the examples, you can kind of see from this example that typically W will be a sum of only very few examples, because W is only a sum over the examples. The only alpha mu's which are not 0 are the ones which are at the margin. So the typical situation that will happen in this problem is that only a few points will lie, at a minimal distance from the plane. And what we already know is that the optimal weights are a linear combination of these points. And intuitively, it kind of makes sense that the points that do not lie, not in a minimal distance, for them we don't care much about the precise direction of W. And this is kind of why it makes sense that it's really the points that end up being, at the minimal distance that determine how W looks like. And this is also why this is called support vector machine, because the points which are at the margin are also called the support vectors. Okay. These are the support vectors. Okay.
So these orthogonal distances that they are the support vectors. You draw the ones you draw.
No, these are the
minimum margin.
The vectors themselves are the x mu's. It's this vector and this vector, right?
Okay.
And the vector W, which is actually perpendicular to this plane, is a linear combination of this one and this one. So let's try to I drew it a little bit small, and let's do it again and see if it makes sense. Okay, let's choose some points. Hopefully, this is not working.
Crosses instead of points.
Okay, now we need to find the plane that will minimize the distance between. Okay, I will do something like this. The plane that will minimize the distance, and I think I'm not absolutely sure, but I think that it will be this one. Okay, now let's make it correct. Okay. So the distance, its distance from here and here is the same, and we cannot, if we move it like this, the minimal distance will decrease. If we move it like this, the minimal distance will decrease. And I don't think that we can find a better solution. So my claim is that the vector, this vector, can be written as a sum, as a linear combination of this vector and this vector. Now in 2 dimensions it's obvious, because we have two independent vectors, so any vector can be written as a sum of them. But this will turn out to be true also in higher dimensions. Okay. Typically the situation will be that the number of support vectors will be significantly smaller than the dimensionality, which is hard to show in 2 dimensions, because 2 dimensions is small dimensionality. But if we have a large dimensionality, typically the number of support vectors will be small, so it's not trivial that the solution is a linear combination of them, but it's true. It's what we concluded from the math. Okay.
Support vector is actually a point.
So the support vectors are this vector and this vector.
So there are only 2 pointers cross vectors?
In this, no, often, so in higher dimensionalities, often you will have a situation where you typically will have more, you need to constrain a plane. So you'll have typically more than 2 support vectors, but nevertheless, the typical situation will be that the number of support vectors will be smaller than the dimensionality.
Won't it be exactly the dimensionality?
I don't think so, but I need to. Well, the number of. No, I mean
Yeah. You could think in 3-dimensional.
Yes.
So you will have 2 points that will determine this plane, but exactly the position of it will be determined by another point in the.
No, still, even in 3 dimensions, just 2 points can determine the whole plane. In 1
Yeah.
dimension, you need 2 points still.
Right. So.
Like,
So
Yeah. Or in one dimension, it's 2 points as well.
yeah, I don't think that the number of support vectors is always 2.
Between 2 and the dimensionality.
Yeah, it could be larger. But I have a hard time.
It can be less than 2, right? Because you have 2 groups.
No, that's right. It can't. I don't think that it can be less than 2 because otherwise you can, you need to be constrained in both, at least more than one direction. So, yeah.
Why do you have the word typically there and giving it through?
Well, I wrote typically because I think that it's you can cook up examples where you will not use one of the cases, but typically this will be the case. I mean, you can't see here from the argumentation that it has to be positive. I don't think that you can see it. If this thing is 0, then it's not obvious that the alpha has to be positive, but it will typically end up being positive. The interplay, the alpha here then enters through the fact that this needs to be a minimum with respect to W. So there is a coupling, there is a term here that involves both alpha and W, right? But it involves all this form. Okay, so let's just summarize what we know about the solution. I will erase this. The solution must obey the following. 1, W is a linear combination of the examples, and the coefficients are the alphas. 2, either alpha is 0 or we are on the margin. So we can write this like this. At least one of these 2 things has to happen. Either we're on the margin and then alpha can be non-zero, or alpha is 0. 3, all the examples should be classified correctly. Now W transpose X is larger than 1 for all mu, and all the alpha mu's are larger than 0. All these are properties that we know have to be obeyed by the solution, and they are also sufficient. I mean, if you find a set of W's and alphas that obeys all these requirements, then it solves the min-max problem that we defined. And again, the support vectors are those vectors for which the alpha mu's are larger than 0, and these are, on one hand, those vectors that contribute to W in this expression, and also these are the examples that end up being at the minimal distance, or to have the minimal margin, or lie on the margin. People say it in different ways. Okay, so now, after all, yes?
Still the complete what exactly we are like minimizing. We are minimizing the distance between the two nearest points.
We remember the initial formulation was that we were maximizing the minimal distance to any point. We're maximizing the minimal distance to any point, right?
Okay.
Then we did all these mathematical manipulations and ended up with this formulation. And from this formulation, we made these conclusions. Okay? So this is now not, here it's not written as a minimization or maximization problem. This is just a set of properties that the W's and alphas should meet, and I claim that it's both necessary and sufficient condition to be the optimal weight. Okay?
Still going to have a graphical or like feeling of alpha.
Well, the alpha is really the coefficient with which, so the weights, which are, remember there's a vector perpendicular to the plane. There are a linear combination of the examples that lie on the margin, that have a minimal margin, and the coefficients alpha are, the weights at which you take them. This is one way to think about them. But yeah, I don't have either a better feeling for what they are. All right. So after having done all this, we're now going to reformulate the problem in yet another way, okay? Which will turn out to be useful. And so maybe I will keep this expression, but I will erase this and this. So So remember that I called the problem that I defined at the beginning the primal problem, and now we're going to meet the dual problem. So the initial problem that I formulated, the primal problem, before I introduced the Kuhn-Tucker theorem, was in terms of the W's, right? And now what we're going to do is we're going to take this expression. We already know what the W's are. I have the expression from here. So we're going to plug this into the expression and get an expression which is just written in terms of the alphas. And we know that we need to maximize this thing with respect to the alphas. So we're going to substitute what we already know for W in this expression. L is equal to I need to write down this thing. So W is this sum. So if I want to take W transpose W, I will have a double sum over mu and nu, alpha nu, y nu, and x mu transpose x nu, right? I would write this W as a sum multiplied by the sum, and then I can just take the sum to the beginning. This is what I will get. So this is this term. Then we have plus sum over mu alpha mu. And we have this term, which is minus sum over mu alpha mu y mu. And here we need to have another index of summation because W is written as a sum over example, so we'll call the other index of summation nu. Sum over nu alpha nu y nu, and we have x mu, and all this is multiplied transpose, all this is multiplied by x mu. And so you can see that the expression that we have here is exactly the same as the expression that we have here, except for the coefficient, which is half here and minus 1 here. So this ends up being minus half sum over mu and nu alpha nu y mu x mu transpose x nu plus sum over mu alpha mu. And I will call this thing Q of alpha. This is now a function only of the alphas. And the examples, but the examples we think about them as fixed. And so, okay, maybe I will, this deserves writing clearly. Q of alpha is half, is sum over mu going from 1 to p alpha mu minus half. And now I would like to do one more step and write it in the following way. Mu sum over mu and nu alpha mu alpha nu y nu, and here I will write k mu nu, and k mu nu is defined as the sum over mu and nu of x mu transpose x nu.
Why sum? Why not only the x?
Sorry, no sum. You're absolutely right. So x mu nu, k mu nu is just the vector, the scalar product of the vector x mu and the vector x mu. No sum. Okay, so so now we know that the alphas, the alphas are the argmax of over alpha of Q of alpha under the constraint that all the alphas mu's has to be larger than 0 for all mu. Why do I care about the alphas? They give us W. If I know the alphas, I know the W. Okay?
So we have two alphas here. No, we have one. No, we have.
No.
How many alphas do you have?
Maybe you should say alpha sum. Better.
Yes, okay. Alpha opt. We used opt before, so we'll continue. The optimal alpha are the ones that obey this equation. So this is another quadratic programming problem. We have here a quadratic form over the alphas, and we want to maximize it under a set of linear constraints. The linear constraints are simple. They are more simple than before. They are constraints that all the alphas should be positive or non-negative. Okay. So what have we done so far? We have some conclusions about the solution, but if we really want to find it, we still need to solve this problem. And so we replaced an n-dimensional quadratic programming problem in terms of the W's, which was before we introduced the alphas. And we introduced the alphas, we got an n plus p dimensional problem. We solved for the W's. Now we have a p-dimensional problem. So we replaced an n-dimensional quadratic programming problem by a p-dimensional quadratic programming problem, which in some sense has an advantage. The quadratic form looks a bit more complicated. The linear constraints look more simple. And often the case will be actually that the dimensionality p will be smaller than n. We will, as you will see, we will be interested in situations where the dimensionality n is very large. So often the case, the number of examples will be actually smaller than the dimensionality. So in that sense, this is useful. And the next thing that I will show you is an algorithm that finds the solution to this problem. Okay, so you had a question?
Okay, so we have the, why don't we have p square alphas? I mean, p squared, and there have the alpha mu and the alpha, there are two alphas here for every.
Well, there is a set of alphas. The number of alphas is as the number of examples. The fact that the sum here involves combinations of them doesn't mean that you know, if you would tell me what is alpha 1, alpha 2, up to alpha p, that's it. The expression is well defined. The number alpha has one index. It's mu.
Okay, but what are we minimizing? What under function of alpha? If all the alphas are set, what are we computing now? What are we trying to do?
This function. We're trying to maximize this function, which is a quadratic form over the alphas. It involves our terms here that look like
two indexes, okay, of
yeah.
the same alpha.
Yes, it's the same alphas appearing here and here. Okay, it's not the two different ones. So there's a term here that looks like alpha 1 squared. There's a term that looks like alpha 1 alpha 2. There's a term that looks like alpha 2 alpha 1, and so on. All right, so we know that we need, if we want the alphas, we need to solve this problem. Then we can get the alphas, and we can also know what are the W's. So the next thing that I will discuss is an algorithm that finds the maximum. This algorithm is called the Adatron algorithm. I don't know why, but this is how it's called. It's a learning algorithm for the SVM, support vector machine. And I will just write it down, and then we will discuss why it works. So the first thing is that you begin with some set of alphas. Let's call them alpha mu 0, 0 for being our initial choice, which all obey the constraints. And the next thing is that we do is that we iterate through all the examples. This is similar to what we did also in the binary perceptron learning algorithm that we discussed last time. Iterate through all the examples.
Choose alpha mu 0, you can just do anything?
Yeah, you can do whatever you want, as long as it obeys these constraints. We iterate through all the examples cyclically through all examples. And what we do in each step is we go from alpha n to alpha n plus 1 based on example x and yn, and the x and y1 and yn are the ones that are chosen, cyclically through all the examples. And this alpha n plus 1 is, I will write it as alpha n plus delta alpha n. This is a change in alpha, and now comes the essential ingredient which is the definition of what is a change that I do in each step. So actually, I will use a different notation here. I will write here x nu and y nu. Where nu is updating each time. So each time we have one particular example that we're looking at, and the change that we will do will be only to the alpha nu. So delta alpha nu will be equal to what I will write. Okay, where delta n nu is equal to y0, y nu, w transpose n times x nu, and w n is defined as the sum over mu going from 1 to p, alpha n mu, y mu, x mu. Okay, so and the other alphas are not modified. So the only one of the alphas is modified. Again, in example n, in iteration n, we look at example x nu. These are iterated through, and we update the coefficient for that example. We don't update the other alphas. So the other alpha mu, where mu is different than nu, left unchanged. Okay, so again, in each iteration we have one example, and what do we do? Example x nu, we update the coefficient for that example, and the update is the expression that is written here. And now let's think about what this does. Delta n nu is the distance, is the projection, on the news example, the new example, the distance of the news example from our current plane. Right, the plane is this thing, and this is a quantity that, remember, needs to be positive. Sorry, negative. Right, this thing needs to be negative. So because we want these things to be larger than 1. What?
In the maximum, yeah.
There is an eta here. This eta I didn't define. This is some quantity which is larger than 0. And we will discuss how things depend on the eta, what are our requirements for eta, or additional requirements for eta later on. Okay? So eta is some constant. I should have said this. Eta is some constant. It's fixed throughout the learning.
Why do we do this serially and not like 1 point at a time, changing index?
I don't know. This is the algorithm.
Not,
This is the algorithm. This is the algorithm. You can think of other things to do, but this is the algorithm. Okay, so let's think about what this is doing. So if delta n mu is larger than 1, this means that the example is correctly classified, and moreover, the margin is larger than 1. And so what will this update rule do? What will this update rule do to alpha nu?
So give it like bring it to 0.
It will bring it closer to 0. It will decrease it, right? What is the role of this part?
It's decrease completely to 0.
Well, not to it's not the point is not to, maybe this will, if eta is small, maybe this will not bring it to 0, but
Yeah.
what does this ensure?
That you'll not.
That I'm not going to make it negative, right? So this part, you can think about it as follows. If the example is has a margin larger than 1, then what we're trying to do is reduce the corresponding alpha. But this part in the rule just ensures that we don't make it negative. So under this condition, what the algorithm is doing, it's reducing alpha nu while ensuring that alpha nu is at least is non-negative. Okay? Now, if delta nu n is smaller than 1, then it means that either the margin is, it means that the margin is smaller than 1. It could be also that it's negative, meaning that the example is not even classified right now correctly. So, correctly, let me write it like this. Not classified correctly. Or classified correctly, but margin smaller than 1. And we want all the margins to be larger than 1. So what is the algorithm doing in this case?
How can the margin be smaller than 1 if it's doesn't that imply that there is some point in...
No, 1 is, remember that 1 is the distance from the, the margin is the distance from the point. So when it's 1, we're definitely classifying the point correctly. We're also classifying points in its vicinity correctly. So you can have examples where there are many, the margin can be smaller. A margin equals 0 is the point where we cross from correctly to incorrectly classified. Okay, so, but we want to be in a situation where all the deltas are larger than 1. So what is the algorithm doing in a situation where delta nu is smaller than 1? What can you say about delta alpha nu? In this case, we reduced alpha nu. What do we do in the case? What does the algorithm do in this case?
Positive.
This thing is positive, so it's increasing. So it's definitely increasing. It's larger. This thing is negative, so this is the maximum. Is this thing? It's increasing delta alpha mu. What the algorithm is doing it's increasing alpha nu, and I claim that increasing alpha nu also increases delta nu. We want delta nu to be larger, and this step is achieving that. Why? Because delta nu, let me just first write it down. This is our expression for delta nu. If we increase alpha nu, then I claim that delta nu increases because the change in delta nu is coming from the change in the W. The change in the W is coming from the change we only change one term here, which is the one that involves alpha nu. So the change in delta nu is y nu y nu again, because y nu appears also in the expression for W. And then we have x nu times transpose times x nu. And there's an eta here. Because alpha mu, the change in alpha mu no, there's no, yeah, the delta alpha nu included also the eta. And is there a minus sign missing somewhere? No, we changed the.
Increasing delta nu is positive.
Yeah, it's positive. Yeah, that's right. So yeah, I should write here just no eta here, but I should just write here delta alpha nu. Delta alpha nu. That's what we needed, right? Does everybody see this? Because I was a bit confused. Is this clear? No? Okay. So what I just wrote is, I'm asking myself, what is the effect of a change in delta alpha nu over delta? What is the effect of a change in alpha nu? This delta alpha nu, how does it affect delta nu? So I see that delta nu is this expression. It's changing because we changed the weights. How did we change the weights? We changed only the coefficient of only one coefficient here changed. It's alpha nu. So the change will be delta alpha nu times y nu, again y nu, x nu, x nu. You seem unhappy, Daniel?
Unhappy, of course.
It's okay? Okay. Okay, so now this thing is positive, right? So indeed, what the algorithm is doing, if delta nu is smaller than 1, it's changing it in the correct direction. It's making it, we need it to be larger than 1, it's making it larger.
What do you mean by the parentheses there, the other?
Well, again, in each step, we take one example, and we only change the alpha corresponding to that example. We don't change the other ones. That's what I mean. All right. So we see that at least the algorithm is doing something reasonable in each step. It corresponds to.
If delta is equal to 1, it's just don't change. Because then, like, the maximum would.
Yeah, I think so, but it's yeah. Well, we don't change. Okay. And this is time for a break. So what we will do after the break is prove that under certain conditions, the only thing that we can play with in this definition is eta. So eta has to be positive, but as you'll see, there is a guarantee that if eta lies within a certain range, this algorithm will converge to the solution. And this is what we will prove after the break. פשוט אני מציג פה את השינוי, צריך לקחת את השינוי לא, אני כתבתי פשוט במונחים של השינוי באלפא, כתבתי משהו. בחרו דלתה אלפא.
זה דלתה אלפא.
גם אותי זה בלבד שכתבתי.
אבל בעצם השינוי באלפא זה בעצם אחד פחות דלתה.
נכון, נכון, אבל ראינו שהשינוי באלפא פיור, זה מה שחשוב.
כאילו אמר, יש לך הרבה תוצאות תוצאות
אני מאוד התחברתי על התיאוריה אלוקית, כאילו, ואז עדיין, כאילו, זה כאילו שמתחילים מהסיפור. הוא אמר, תראה אם יכול להתנסה לראות משהו שקורה בדיוק פיסטים, שם זה היכולת לשנות את
נראה לי גם, כי
זה מה שמעניין. זה כאילו מתמטיקה סופר.
זה הסבל שלך, אני מדבר על הסבל של הכל. אולי הם ליצורים
לא, לא ספר, אבל יש
היום הראשון היה די שוק מהגודל של
לא אמור להיות פה לי? כמה זה תקנה בלי? או שזה, לא, פשוט בכתוב. כי אנחנו נשנה בכל איטרציה רק את האלפא eta, נכון?
לא, לא, מיו. מיו. כן, אנחנו משנים את האלפא מיו.
לא,
אוקיי. אנחנו משנים, כאן כתבתי את זה כווקטור, אבל באמת הוקטור הזה הוא וקטור שיש לו רק ערך אחד ששונה מערך.
אני יכול לשמוע פה פשוט במקום וקטור.
כן.
והחלק הזה הוא בעצם חלק מהפרק.
החלק הזה הוא דואג שזה לא יהיה יותר מדי שלי.
לא, במקרה הרע הוא פשוט...
לא בהכרח, כי בעצם...
הוא בדרך כלל קורני.
יכול להיות שזה מספיק, בערך מוחלט מספיק קטן, שזה לא מוריד לשם. אני חושב שיש לנו נורא קטן. אז כל פעם אתה תעשה איזה צעד קטן, ואתה לא תגיד. אבל הדבר הזה דואג, שאם אתה מנסה לרדת מתחת לאפס, אתה תשאר.
אולי אני לא צריך פה מה אפשרי לרשם, אינסופי, וכן אישור הרשמה, אתה המלצה.
כן, אני חושב שאתה יכול לעשות הכל. בוא נדבר על זה, נעבור על זה בקצרה.
אבל הוא כאילו נצפה סתם, הוא כאילו יצא לא, סתם אתה רואה לא, הרבה פעמים, כאילו אתה אפשר כזה להסתכל על עבודה, קודם כל זה מוסיף ואז כל שם כן,
פה זה פשוט מקלה.
מה השאלה?
זה
לא, כאילו מה בדיוק?
מקסימום.
זה לא מתמשך. בעצם לא תלוי. אם זה חיובי, זה לא היינו רוצים לעשות את זה. זה ממש כמו שהגיוני. שאם הדבר הזה שלילי, אנחנו
רוצים לקדם כל אחד
הדבר הזה חיובי, אנחנו רוצים להקטין את האלפא. למה? כי אנחנו יודעים שבפתרון הבעיה, אותם דוגמאות שהן לא על המרג'ין, שהן לא במינימל מרג'ין, האלפא של הקורטקס. אז אנחנו רוצים להקטין את האלפא במקרה שזה חיובי. שזה ממש חיובי, אנחנו רוצים להקטין את האלפא. אז אנחנו מקטינים אותו, אבל זה דואג שאנחנו לא נקטין אותו מתחת לאפס.
ויש המון סימפוזיונים
שזה ממש חיובי?
ששם כאילו יש קורלציה של ההוצאות כאילו ההוצאות העולם
כשזה ממש חיובי.
כשזה פחות זה חיובי, זאת אומרת שזה שלילי. כשזה שלילי זה אומר שאנחנו רוצים להקטין את ה... לא דווקא, אנחנו מקטינים, הדבר הזה משהו שאנחנו מקטין את האלפא. והדבר הזה דואג שלא נקטין אותו יותר מדי ככה שהוא יכול להיות שלילי. נכון, נגיד כן, כי הכי הרבה שאנחנו מרשים לאלפא לקטון זה הגודל שלו המדויק. נכון, אם אנחנו מנסים פה להקטין אותו, נניח שהיינו מנסים פה להקטין אותו משהו שיותר גם מהערך שלו, אז הדבר הזה ידאג שלא נעשה את זה, שנשאר אותו בעצם. עכשיו זה רק בכיוון של להקטין את האלפא. ואם הדבר הזה הוא חיובי, זה אומר שזו דוגמה שאנחנו עדיין, שהיא לא בסדר, היא עדיין לא, או שהיא לא מתשווקת נכון, או שהיא מתשווקת נכון, אבל המרחק שלה הוא קטן לאחת. ואז ראינו שהקודם אם הדבר הזה חיובי, אז זה בכלל לא חיובי, זה חיובי, זה לא רלוונטי בכלל. ואנחנו מגדילים אותו, וראינו שהגדלה הזאת פועלת בכיוון הנכון, במובן הזה שהיא מגדילה את ה... שהיא מקרבת, היא מגדילה את הדבר. מגדילה את הדרך.
איזה דוגמה של תהליך, אבל שאולי כאילו שנעשה את התרגיל.
based on some questions that I was asked, I would like to just go through things once more, just to follow the logic of what I told you. First of all, in terms of what the algorithm is doing, then I wrote here the change in alpha as a vector, but it's a vector which is very special because only one entry in this vector is different from 0, and this is the entry corresponding to the particular example that we look at. So this is what is written here. Only that alpha nu is changing, the other ones are not changing. And the other thing, in terms of just of the logic of what I wrote here, then I pointed out that the algorithm is doing something that makes sense. If our example is one which is correctly classified and moreover the distance is larger than 1, then we saw that what the algorithm is doing is it's reducing alpha nu. Why does that make sense? Yes, but how do we know that that's what we want to do?
Because we remember that we want the W optimize that only for the alpha.
Exactly, because we saw earlier that for the optimal solution, indeed the alpha nus are 0 for those examples which lie beyond the minimal margin. So it's doing the right thing, and what we see here is that in this situation, I mean, it's reducing alpha nu because under this condition this thing is negative, and what this term is doing, this is something negative and this is something negative, it just ensures that we're not reducing alpha nu by more than its magnitude. We're never allowed to reduce alpha nu beyond the point where it's 0, such that it will become negative. So this is what this is doing. The other situation is an example for which currently we're not achieving what we want. It's either incorrectly classified or it's correctly classified but with a distance smaller than 1. In that case, this thing is positive. This thing doesn't matter because the maximum of a positive thing and a negative thing is this. So we're always increasing delta alpha nu. And again, what I've showed you is that the algorithm is doing something sensible in the sense that the effect, the consequence of introducing this delta alpha nu on delta nu is that delta nu increases. So we have a problem, this delta nu is smaller than 1, and we're doing something which will bring it closer to 1 or maybe larger than 1.
If it's not classified well, why is it the fault of alpha nu?
Well, I don't know if it's a fault of the alpha nu, but I do know that we're going in the right direction, that based on the change that the algorithm is doing to alpha nu, is going in the right direction. It's true that if you will change the other alphas, it might also change. So it's not obvious that this algorithm is going to work. I'm just showing that it's doing something sensible. Now we're going to prove that it works. Okay? So, first, before I start writing down equations, I want to think about the quantity that we're trying to maximize. So remember that we're maximizing a quadratic form over the alphas. And it's not just a quadratic form. So I had it written before, but it was erased. So let's just write for a moment the quadratic form again. Q of alpha is equal to sum over mu, going from 1 to p, alpha mu, and then it's minus half sum over mu and nu, alpha mu, and then it's multiplied by y nu, k mu nu. I think I had the mu and nu at the bottom, so I will keep it. And k mu nu is equal to x mu transpose x mu. And so we have here, in the space of the mu's and nu's, we have here a p by p matrix, right? The matrix. So y nu, we could have written this thing could have been written as alpha transpose minus half alpha transpose some matrix y mu, y nu, k nu nu, alpha transpose. This sum can be written in this way, and this matrix, I claim, is positive definite. I will not show it. It's very similar to how I showed that in the last week that some other similar matrix was positive definite. You want to show that whatever vector you put on its two sides, you will get some non-negative answer. Okay? A positive answer. So this matrix is positive definite, and what this implies is that this quadratic form has a maximum. Okay? We should have said it already before. Our problem was defined as maximization of Q of alpha. How do I know that this thing has a maximum? It's because this matrix is positive definite. So in the p-dimensional space, we have some kind of paraboloid with a maximum. This is the largest value that Q can assume. Is it going to be the value of Q at our, at the solution that we find? So I'm saying that this quadratic form has a maximum. Is Q going to end up being at that maximum? Not necessarily. Why not? Because we have something in addition to the requirement of maximizing Q of alpha. Yeah, so we have a constraint. We're trying to maximize this function plus, constraints on alpha. That alpha mu is larger than 0 for all mu. So it could be that this point does not obey all the constraints. So typically the situation, just if you think about it geometrically, is that we're trying to maximize this paraboloid in some space where this is drawn in the space of alphas. So I don't know, imagine that the alphas are like this, the origin is here, then this point is not allowed. It has a negative, this alpha, alpha, suppose that this is alpha 1, this is alpha p. Alpha 1 at this point is negative, so we cannot reach, typically we cannot reach the maximum. We'll reach some point which, is the maximum given the constraint. But there is, the important thing is that there is a maximum, okay? This is, the quadratic form does have a maximum. Yes?
Can you explain the dimensions of the object y, y, k? Because k, mu, nu is the scalar. No?
Well, it depends on the number, on the indices mu and nu.
How comes it?
Well, you see explicitly, it has two indices on it.
Okay,
So it's, for each mu and nu, it's a number. But if I think about this as this lives in the space of the mu's. So I see what you're saying. I should have written here.
I see what you're saying. That's like a
Yeah. But I should have written here a matrix and said this is the indices of this matrix. These are the indices of the matrix.
For space mu,
Yeah.
that's the.
Okay. Let's be more. Let's be a bit more. Rigorous and write this as a matrix alpha, and a mu nu is y mu, y nu, k mu nu, and this is positive definite. Thanks for the comment. All right. And so minus this matrix is negative definite. It has a maximum. Any quadratic form which involves this matrix has a maximum. And again, geometrically, we're going to end up with some position which is the maximum of this quadratic form given the constraints on the alphas. Now, one of the reasons I'm mentioning it now is that what we will do in the proof is that we will show that in each step, in each one of these steps, Q increases. Okay? And if we know that in each one of the steps Q, as long as there is an update, okay? And if we know that, and therefore we know that it has to converge to some, because this form has a maximum, and we're increasing each time, we will have to converge to some steady state. So we know that, and then we will see that if we are at a steady state where we're not updating anymore, then it has to be a solution of the problem. So this is the idea in the proof, and then now we need to work on the math. And so what we need to do is to calculate delta Q in each step. This is what we're going to do. And I'm going to, just to make life more pleasant for us, I will not write down explicitly all the n's, each time, the alpha n plus 1. I will just write delta Q, the change. I will omit the n index. We're at step n, we're doing one update. What is the change in Q? This is what we want to do. So Q is a quadratic form, so we can write down the change in Q in terms of the change in the alphas, right? So let's do it. Delta Q. So we have here a sum over all the mu's, but remember that if we're looking at the example mu, we're only changing alpha nu. So the only one term here will change, so one change in delta Q will come from here. This will be delta alpha nu. And then we need to write down the change in this quadratic form. So now this is a bit confusing in terms of the indices. So if you want to do it carefully, you don't want to have here a nu, because I already used the nu for the index which is being changed. So it would be better to have here a mu and some other letter. Chi. How do you write? Chi? Okay. Okay, fine. If you want the chi, it will be a chi. Okay. So now there are several contributions to the change in Q. One will be from, when mu is equal to nu, and I multiply by the alpha here without the change, with all the alphas here without the change. So what will that give us? That will give us minus half sum over chi, alpha chi, y mu, y chi, k mu chi, times delta alpha nu, right? So this is the delta alpha that came here. There will be another term where I do this here, but it will give me essentially the same thing. Well, we can write it down and see, but it's going to be the same thing. It will be sum now over mu, and now chi is the one where we're considering, instead of, here there's alpha mu plus delta alpha nu, so I take the delta alpha nu. So there will be alpha mu, y mu, y nu, k mu nu. Sorry, here, this mu was a nu, right? So this was nu. Right here, in this case, I picked the case where, mu is equal to nu, and there was a delta alpha nu here. There will also be this term, so sum over mu, alpha mu, y nu, k mu nu. And times delta alpha nu. And so now you can see that this thing is exactly like the same as this thing, because we don't care if we call the summation index mu or chi, and k nu chi, or k nu mu, k is a symmetric matrix. So this is why these two terms are the same. And we're left with one more term. The term that is left is remember here we have, if both indices mu and chi are new, then we have here alpha nu plus delta alpha nu, and here we have alpha nu plus delta alpha nu, so there's a term where we pick the delta alpha nu in both of them. Okay, so this will give us minus half delta alpha nu square times y nu square, right? Y nu, k nu nu. So this is the change in Q, and I want to prove that this change is positive. So let me write it down again. Delta Q is equal to delta alpha nu. I will just use the fact that this is the same as this. So we have here minus sum over mu alpha mu delta alpha nu times y nu. And here I would like to write now explicitly what is k mu nu, so I would write it as x mu transpose times x nu. And then we have here minus half delta alpha nu.
Is not equal to mu, right? Like the previous.
No, the mu equal to mu also participates. It's not the same thing as this term, as the third term, because here this is the cases where I take, here you could have the case where this is nu and this is nu. You take the delta alpha nu from here, and here you just take the alpha nu. So this is this term. It does participate here, but then the one where you take the delta alpha nu in both is another term. So, and here, so we have y nu, actually y nu square is 1, so I don't need to write it down. This thing is just 1. And so here it's just k nu nu. All right, this is the change in Q.
Can you please explain again why don't you have a sum in the third term?
Yeah, because the only way I can get something quadratic in delta alpha nu is if delta alpha nu appears both here, delta alpha appears both here and here. But only the indices nu changed. Only for indices alpha nu changes, alpha mu changes only if mu is equal to nu. Alpha chi changes only if chi is equal to nu. So the only place where you have a delta both here and here is when both indices are nu. Right? Okay, now, actually, this thing is, it involves some familiar quantities. Where I claim that this thing is delta alpha nu times delta alpha nu appears both here and here, and then it's times 1 minus sum over mu alpha mu x mu x transpose. I claim that this is delta nu. Okay, so actually I think we never wrote down explicitly delta nu in terms of the these quantities. So let's do it now. I want to use the same notation that I used before. Where do I have it? Okay, so delta nu. Okay, delta nu is y mu W transpose X mu, but W transpose itself, W, remember, is a sum over mu, alpha mu, y mu, x mu. And therefore, I can write down delta nu as y sum over mu, alpha mu, y mu, let's put this here, y mu, x mu, transpose dot x mu. Okay, so this is exactly what is multiplying here delta alpha mu, delta alpha nu. Sum over mu, alpha mu, y mu, x mu, x mu. Exactly what you have here. So this is what we have in this term. And then we have the second term, minus half delta alpha nu square k mu nu. K nu nu, yes, k nu nu. Now, there is one interesting thing to note here, and okay, remember that what was delta alpha nu? Delta alpha nu, unfortunately it was written in this part of the whiteboard, so I will write it again here. Delta alpha nu was the maximum of minus alpha nu and eta times 1 minus delta nu. And imagine now a situation where eta is very small. So eta is actually, what does eta control? Eta control how fast we're changing the alphas, right? The smaller eta, the smaller steps we take each time. So in the limit where eta is very small, what we're actually going to, then the delta alphas are also small. And therefore, in that limit, we can forget about this term. In the limit where eta is very small, this term will be small compared to this one, right? And what is nice about what you see here now is that if we have a small delta alpha, what this calculation tells us actually is that dq to d alpha nu is 1 minus delta nu. Right? I mean, actually what we did here is we just asked how does q change if we make a small change in alpha nu, and in the limit where alpha nu becomes small, then the linear term is really the derivative. So what this calculation tells us is that the q to the alpha nu is 1 minus delta nu. And you can see that the Adatron algorithm, when eta is small, is just changing it's changing the alphas in a way which is proportional to the derivative with respect of q with respect. It's changing each alpha in a way which is proportional to the derivative of q with respect to that alpha.
Can you repeat that?
Yes. On one hand, you see here that, so imagine again that eta is very small. In that case, suppose that you do one cycle over all the examples. Each one of them will change in a tiny bit, so we don't need to worry about the fact that when it changes, it also influences the change in the next one. Essentially, what we will get is that the change in each one of the alphas will be, some very small number times 1 minus delta nu. And now what we see from this calculation is this is also equal to the derivative of q with respect to alpha nu. So what is the geometrical interpretation of that?
How did you get it without this calculation?
No, I got it from the calculation. I see this from the calculation that delta Q for small delta alpha nu is, the linear term is this thing. So this means that the derivative with respect to alpha nu is 1 minus delta nu. Now, so conclusion, so what I claim is that if we now compare this to the Adatron algorithm, we see that when eta is going to 0, the change in alpha nu is proportional to dq to the alpha nu. What does that mean?
Delta alpha nu, the first one, the big delta?
Yes, big delta. What does that mean? So we have some function of the alphas, and we're moving in the direction which is this. What is this direction? How is this called? This vector. We have a function of all the alphas, and we're taking a vector which is, each element is a gradient with respect to alpha nu. What? It's a gradient. I said it actually. Okay, it's a gradient. This is the gradient of Q with respect to alpha. So you see that when eta is small, what this algorithm is just doing is going in the direction of the gradient. Except that it's almost true. You should have told me that what I'm saying is not precisely true. It's true as long as this alpha is not 0. If alpha is not 0, this algorithm is not allowing it to become negative if the gradient is negative. Okay? So it's gradient up to the end constraint. It's gradient, and what this algorithm is doing when eta is small, it's going in the direction of the gradient, but if it hits, if in the space of the alphas, we had this picture here. In the space of the alphas, when we reach this point, it's not going anymore in this direction, which is the direction of the gradient. It's going in a direction like this, because it's not allowing alpha 1 to become negative. So this is not the proof that the Adatron algorithm converges. We'll now continue with the proof, but this is just a side comment that we can see from this analysis that for small eta, the Adatron algorithm goes in the direction of the gradient, and this is a very well-known form of learning, gradient learning. You go in the direction in which Q increases the most. Okay, now let's continue with the proof. What I should mention before is just what am I proving? Because I didn't tell you anything about eta. So I will write down the theorem here, and then we will continue with the proof. So the theorem states that as long as eta is larger than 0 and smaller than 2 over the following quantity, the maximum over mu of the magnitude of the example mu, the Adatron algorithm will converge. To alpha mu. That satisfies the dual problem. Okay, so you will see later that we will need also this assumption that eta is not too large.
The parameter is alpha mu or square? Or 2?
2. This is 2. Sorry. Okay, so continuing with the proof. So now we will consider two cases. One, if 1 minus delta nu is larger than 0, so these are the cases where delta alpha nu is positive. It's equal to eta times 1 minus delta nu. And we can plug this in this expression. Then delta q is equal to eta times 1 minus delta nu square minus half 1 minus delta nu square here, minus eta square 1 minus delta nu square times k nu nu is x nu square, and this thing I can write down as eta can you read what I'm writing here? Okay. So eta times 1 minus delta nu square. This appears in both terms here. And then we have here 1 minus magnitude of x nu square times eta over 2. And now you see why I needed this assumption. Because of this assumption, this is necessarily positive. Because for all the nu's, eta is smaller than 2 over x nu square. So so the fact that we're going in the direction of the gradient means that if eta is very small, we're always going to increase delta q. But because of this nonlinear term here, if delta is too large, then we might run into problems that we're actually ending up reducing it. But if we keep eta sufficiently small, then we're guaranteed to increase q. Okay, and now the second case that we want to look at. So I continue here. The second case is the case where 1 minus delta nu is smaller than 0. Okay, so here we have to be more careful because we don't necessarily know what is delta alpha nu. It's either this or this, depending on which one is larger. But what we can say is that delta alpha nu is at least as large as this, right? Delta alpha nu is at least as large as eta times 1 minus delta nu. This is a negative quantity. This is a negative quantity. And at most it's changing with this. Maybe it's changing less because maybe this is too much. Maybe if this is trying to make alpha negative, then it's changing by this. But this is true. And so what can we say based on that? What can we say about delta alpha nu square, which we need because it appears delta alpha nu square will appear here. So what can we say about delta alpha nu square? Okay, so I will write down and then I would like you to think about what you said. Is this what we can say?
No.
What? It's negative, so we have to flip the sign. Yeah. And therefore, we can say that delta Q, which is written here, it's written here. So, this is negative. This thing is negative. Delta Q something here is confusing me now. I want to say that it's at least as large as eta times 1 minus delta nu square, but I don't see why this is correct, because this is true, but it's multiplied by something which is negative. Okay. No. Yeah, okay. Yeah, so no. Sorry. Delta alpha nu is larger than this, and we're multiplying with something negative, so I don't see how we get, this is in my notes, and nobody ever told me that I have a problem in class, but now I see that maybe there's something which doesn't make sense. Okay, let me write down what I have in my notebook, and then we'll think about it together, because I think I see here a problem. I said that delta alpha nu is at least as large as this.
Maybe that delta alpha mu is also negative.
Delta alpha nu itself is negative. Thank you. Yes. Okay, so what was confusing is that I was thinking, we're multiplying it by something negative, so this flips the sign. But it's I think that this is correct. Is it correct? So when you multiply, so minus delta alpha nu is positive. Minus delta alpha nu is positive and smaller than let's think about it in another way. Okay, delta alpha nu times 1 minus delta nu is equal to minus delta alpha nu, which is a positive thing, times delta nu minus 1, which is a positive thing. And minus delta alpha nu is smaller, minus delta alpha nu is smaller than eta times delta nu minus 1. No? So, no, so I'm still, no, still something here.
Yeah, but it's larger than 1 minus delta.
And so this whole thing is smaller than eta times delta nu minus 1 squared. No?
Because again, in the right side there is a minus delta nu.
What? I'm saying this delta alpha nu times 1 minus delta nu is minus delta alpha nu times delta nu minus 1. This is positive. Minus delta alpha nu, we just wrote that this is true. So minus delta alpha nu is smaller than, you know, than this thing. And so,
It's smaller than eta 1 minus delta nu. Not delta nu minus 1.
No, it's still less than.
no, so you have to take the minus on both sides. And therefore, minus delta alpha nu is smaller than this, and then eta, and then we get here, you know, this thing is eta times delta nu minus 1 square, which is also the same as eta times 1 minus delta nu square. And my problem here is that I want an inequality in the other direction. I want it larger than something. I want to show that delta q is larger than something. So what can we do? I think, you know, either I'm confused and you're confused together with me, or there's some problem here. So what can we do? We also know that delta alpha nu is limited by alpha nu. So let me see what happens in the next step. You don't see the problem?
It's fine.
No, I mean, this is...
It's just, if you just address what they're like, delta q is delta alpha mu times 1 minus small delta mu. Like,
Where should I look?
the blue to the left of that, no, up. Yes, okay, so you're looking at the first term.
Yes.
So you have just delta alpha mu is larger than eta times 1 minus
Yes, that is
delta
true.
mu. And then just keep multiplying that by 1 minus delta mu and you have what we wanted.
But my problem is that I'm multiplying by something which is negative.
It doesn't matter, I think. Because you're also
look, look, 4 times minus 1, is it larger or smaller than 3 times minus 1? It's smaller. So, you know, when you're multiplying by something negative and you're increasing, you're increasing this, you're decreasing.
But it's not 4 because it's negative also.
It's negative also, but delta alpha nu, you're saying it's positive. So how, no, but, okay, either I'm, you know, so let's, tell me where I'm doing something wrong. I'm writing, again, I'm writing delta alpha nu times 1 minus delta nu. This is the quantity that I want to address, right? Okay, I'm writing it now in this way. Minus delta alpha nu times delta nu minus 1. This is positive, right? Minus delta alpha nu, delta alpha nu I know obeys this. But this is negative. No. This is negative. This is negative. So maybe it is true that, so maybe minus delta alpha nu no. This is a negative quantity and this is a negative quantity. So this by absolute magnitude is smaller than this. And this is why this is correct, right?
But if you define it as...
And now wait, so now I just write this thing here. So I have here, what I have is that this is smaller than eta times delta nu minus 1 squared. Okay, so.
If delta alpha mu is the maximum of minus alpha blah blah, then minus delta alpha mu is the minimum of the minus of the two stuff inside it. Or maybe I missed.
Fine, but how does this...
And then you have delta alpha mu, like minus delta alpha mu is larger than eta delta mu minus 1. Because like if delta alpha mu is equal to the maximum of two things, then minus delta alpha mu is the minimum of the minus of those two things.
Oh, wait. But you have delta Q is larger than delta alpha mu times 1 minus small delta mu. Right? That's true. You have that.
Delta Q?
Delta Q is larger than the left side.
Yeah. Well, it's... Yes.
Because the right side is positive. So then down.
So you want to just throw away this thing?
Yeah.
Okay, maybe this will work.
And then delta alpha mu is larger than, it's negative, but in the angle it's larger than eta times 1 minus delta mu. So you can just delta Q.
Good. Okay, so I think this course has been taught several years with incorrect proof. But, let's see if this works. So again, so we're in the case now where 1 minus delta nu is smaller than 0, right? And you're saying delta Q, instead of doing all this, we just throw away this term. Delta Q is at least as large as delta alpha nu times 1 minus delta nu. And you're saying delta alpha nu...
Why? But that one is negative.
Doesn't matter.
Smaller.
So it's larger. It's larger than what it would be if we would subtract it. Okay? We have here a negative term. If I would not subtract it, we'll get something.
I think it's opposite. No?
No, it's okay.
dq with this term is smaller than the term, the dq without
Yeah.
this term. Right?
Delta Q.
Like, let's say it's 5, minus 5, okay?
Yes.
So, the previous delta q was like x minus 5. The new delta q will be x. So it's bigger.
Yeah, it's smaller than this because we subtract. No, that doesn't work. We can't just throw away this thing. Delta Q is smaller than this thing. It's this thing minus something negative. So this doesn't work.
Why is it negative?
Because you have here something, the square, and this also is the norm of the vector.
So it's positive. So it's,
There's a minus here.
yeah, minus something positive.
Yeah.
Minus something positive, then Q is smaller than this term.
Maybe 3 could be in a
Yeah, I think so too. So look,
minus solid number, solid 3 multiplied by minus 1. If you do with negative number, minus solid minus 3, it will be...
okay, I apologize. I think that either I'm confused or there's some error in my notes, but I'll figure it out offline, and we'll finish this on Thursday. You can think about it too and show me.
PhD.
I see.
Yeah.
With whom?
What?
With who?
No, I didn't choose
I see.
supervisor. Yeah.
I see.
So yeah. So I hear from Roy that you are teaching about something like data mining stuff and
Like what?
data mining.
No, I don't.
No, but she told me that. So you teaching about PCA or
That's true. My course, part of it, we discussed PCA and ICA.
okay.
Yes. But it's not so much from the point of view of methods for data analysis. We discuss it more as proposals for what the brain might be